Okay, today we will talk about see yesterday we actually ended up in what is called equation of motion. Okay. Now, the equation of motion we actually had, I will just write it again. It was something like y v v plus a minus I think y v dot minus y r minus m u 1 r minus this was one, there is a sway and we had see we had these two set of equations yesterday that we have found out represent a body or a shape moving initially along a straight line and was disturbed slightly. They are governed by this equation when v and v dot r dot sway velocity, sway acceleration, yaw velocity, yaw acceleration. Now, what is meant by stability criteria, and of course, I will talk about the hydrodynamic derivative also, is that first of all, if you see that this equation, you see this is the velocity. In fact, let me put a different color. This one, this one, this are the two velocities and two acceleration. This is my rigid body mass, this is my rigid body mass, this is my rigid body moment of inertia, these are rigid body mass, okay. So, I have got the blue ones, let me put them as blue, this rigid body mass, this is rigid body mass term, this is rigid body mass and the geometric term, rigid body mass and center of gravity, then rigid body mass moment of inertia, rigid body mass center of gravity, velocity, like this. These other terms that comes in the equation are this one, this one, this one, this one, this one, this and this. These are what we are going to call them hydrodynamic derivatives, and I will explain the concept behind that the term why it is called hydrodynamic derivatives. But before that, these two things which are interrelated. You see, the solution for that equation, if we can find out, we may not be able to find out the exact nature, the numerical value, but the nature of the solution would tell me if the shape is going to be stable or unstable. How? Because it has got here something into v, something v dot, something r dot, something v, something v dot, something r dot. This is what is known as a set of linear differential equation, some kind of equation. Now, from there if you can tell how v and r changes with time, that tells me whether the shape is going to be stable or unstable. I will discuss that again, but normally what happens, first of all people write this equation in a non-dimensional way, because if you see this equation, m etc., m is mass of the hull, so it is like maybe 20,000 tons, u may be u1 may be something like 15 knots, this becomes all dimensional values. To make it non-dimensional, which makes it easier, because first of all remember that all of them must have same dimension. So, you see m into v dot, let us look at the dimension part of it, m into v dot is mass into acceleration, which is actually the unit of force. Therefore, all of them must have unit of force, y v v etc. should have unit of force. Okay. But then it becomes sometimes difficult to write them in a dimensional form. So, what people do is that first we will sort of write them in a non-dimensional form. So, so that everything is divided by some non-dimensional form, and then the non-dimensional form, the ease of it is that the numbers are of same order regardless of the ship size, and in fact for a same scale ship it will be same. You know, if you take a geometrically scale ship, it will be same numbers. It is exactly the same as trying to tell you resistance coefficient instead of the resistance R and C. Now, the non-dimensionalization that is done, this is done with respect to normally rho, L and V. These three are used to non-dimensionalize, that is density, which will see, you remember that all of them has the 3 unit mass, length and time. Most you know, like all parameters, at least in what we talk, will have a dimension of either mass or length or time, this 3. So, this will have a mass term here because it is mass by, you know, L cube. This is of having length, this will have the term T. So, normally these 3 are used combination of them to non-dimensionalize. I will actually show only few of them because there is a whole lot of non-dimensionalization, no point of showing that. For example, mass. First of all, we use the word dash. In our student days, we used to call the subject is full of dash and dot, you see. The dash will represent non-dimensionalization. Whenever we put a dash here, non-dimensional. So, this is actually m by half rho L cube. This is how it is defined normally. There can be other ways. Similarly, V dot is not V dot, I am sorry, it is V by V, that is V dash is, and V dot is V dot divided by, see if you see that V dash is V by V because it is meter by second goes away, V dot is meter by second square. So, this has a unit of, see, V dot by V into V by L, that is why it comes V dot L by V square. See, when there is a time there, then L by V square comes in. It very easily you can see, if you want to combine these three to non-dimensionalize with acceleration, it will always become acceleration by V square by L or into L by V square, something like that. So, similarly, Iz dash will become, always this half is used for some convention, like they are also half rho S V square, this half has somehow come to stay. Okay. Then R dash becomes, again this is R L by V, you will find, then R dot dash becomes R L square by V square, it will become. These are the mass and the velocity parameters. Then let us say Y dash V, this will become Y V divided by half rho L square V, Y R dash will become Y R by rho L cube V, then N V dash becomes N V by half rho L cube V, and N R dash equal to N R by half rho L 4 V. I will just tell you an interesting point of like that. You see, if you see that, you will see there is an L square V, L cube V, these two remain same, L cube V, L 4. There is an increase of whatever this into L, this remains same, another L, this L cube, L 4, L 4, L 5. It is actually easy to work it out. You can, if you go through that, you will find it is quite easy. And now x g dash will become x g by L. U1 is basically dash is U1 by V, which is equal to 1, because you see V is actually the forward speed with a small change. Basically U1 will be V, U1 equal to V cos beta or cos of heading angle, but the heading angle is taken as a small, so it becomes equal to 1. see, in other words, u1 is v into cos of the angle of attack, which is equal to v. So that u1 by v becomes equal to 1, you know, when you take a dash part. In other words, okay, this I will tell you in the next slide maybe why it is so. See, whenever we are talking of a shape here, this is my u1, this is my v, this is my v, this is my beta, u1 equal to v cos beta and v equal to v sin beta. Beta is small, u1 v equal to beta. Sorry, no, yeah, v equal to sorry, v beta. So this is what we do, because normally the heading angle will be small, you know, you do not have a ship going like this 45 degree angle, it will be maybe 10 degree or so. Although I write for the sake of this thing, a ship will not travel like this, you know, it will travel with small angle only. So beta is normally 10 degree or so, not much, unless you make a very large simulation. Remember here, of course, it is even small because we are looking at only small perturbation. Remember, ship was going initially along a straight line. You have given a small perturbation. Obviously, it will make a small angle. It is not making a 20 degree angle. Then it is going away very far from your initial equilibrium. Therefore, to make an assumption that beta is small for this so called linear equation. See, these equations are linearized anyhow. The very word linearized equation implies that v dash is small, v is small. V small means that sin beta is small, means beta is small. So this is very, I mean, what I am trying to say, that this is very consistent. There is no ambiguity here, because we are looking at small values of v, small values of r, etc. It automatically means that beta is small. You cannot have large beta, because if it was large beta, you couldn't use this equation up to only first order. Then the Taylor expansion had to go for higher order. Anyhow, so having said that, this I hope is kind of clear. Then we can write these equations in non-dimensional form, and the non-dimensional form simply becomes, it will become all that happens is it gets two dashes here. There I had, let me see one equation. See, u1 was there, the u1 has become 1, that is why this, it's the m u1 has become just m dash. And this is, this is minus. It is not very important that now, if you look at that, see, I can call this to be, I can tell you one thing, that these equations as look at this v dot and v, I can write them in a form that a into v plus a1 into v plus a2 into v dot plus a3 r plus a4 r dot, something into v plus something v dot, something into r plus something r dot. Isn't it? See, here I have got, look at that, this should have been written in a different color. I have got here, these two are coming here, these two are coming here, these two are coming here, and these two are coming here. So it is something into v plus something v dot plus something r plus something r dot, something v, of course non-dimensional, something v dot, something r, something r dot. We can do actually even better. You see, v dot dash equal to dy dv dy dt of v dot of v dash. In other words, v dot dash equal to dy dt of v dash, r dot dash equal to dy dt of r dash, etc. So, what happened, I can write this, you see, if you write it in a more form, then it turns out that supposing I call it A1. So, I can write this to equation, I will just write that and then tell you. I can write this as like this, d by dt plus A2 into v dash plus b1 d by dt plus b2 into r dash equal to 0 and A3 into d by dt plus A4 v dash plus b3 into d by dt plus b4 into r dash equal to 0. You see what we have done. Now, this is interesting. What we have done, see, I wrote that first, I can show you. This is m dash minus y v dash, this term, okay, this is A1. A1, see here, this is my A1 into d by dt of v, that is this term, you see, and A2 is this. Similarly, B1 is this, B1 is this, B2 is this. So, we have simply written in a, never mind the mathematical manipulation, etc., but what I mean is that this is an equation. How does the equation look like? You see, the equation look like something into d by dt of x plus something into x equal to 0. Basically, this is how the equation look like. There are two terms like that. This would have been one term, but I have got something into d by dt x into something into x plus something into d by dt y plus something to y equal to 0 and another one like that. So, I had two set of equation with two unknown, but the two unknowns are related. I have got, you can say, four unknown, v dot v, r dot r, but v dot is dv by dt, r dot is dr by dt. So, if I invoke that, I end up getting something d by dt into v dot plus something into v dot, v dash plus something into d by dt r plus something into r, something into d by dt v, something into v, something into d by dt r, something into r. We can write in this form. As I again say that never mind the exact mathematics part of it. The reason of writing is this way is that this kind of equation will have a solution where you can express v and r in terms of an exponential function, just like in any differential equation. See, we'll come back to that. Now, you look at an equation something like this, you know, that d by dt of x plus, you know, some a of d by dt plus b equal to 0. What people will do, you will assume a solution that x equal to x1 into e power of something like you know, e power of sigma t or something, and then you will try to find out what is my x1 and sigma, because it is, or you can have actually d square by dt square or d by dt, whatever. Whenever there is a differential equation, you assume the solution to be having an exponential form and then try to find out what is the root. That can be imaginary. In fact, if it is a double, it becomes imaginary, means it basically it becomes sine. If it is not imaginary, it is exponential. These are all very standard parts, so we need not worry about that. Okay, we need. My purpose is not also to kind of sort of give you a detailed discussion on solution of linear differential equation. But what I want to say is that when I look at that, I have got two parts. These are all differential equation with the differential coefficient. It is very well known that you can express the solution in terms of a combination of exponential function. It is known that for this equation you can write the solution as, the v can be written as v1 e to the power of sigma 1 t plus v2 e to the power of sigma 2 t, and r can be expressed as r1 e to the power of sigma 1 t plus r2 e to the power of sigma e to the power of sigma 2 t, where sigma 1 and sigma 2 are called roots of a characteristic equation, which is looking like this, but this is formed by taking a determinant of that. Actually, I will just tell you, that I mean this is all very standard stuff. See, if I write this equation again, I will write this in a matrix form, that will be easier. See, we look at this equation. Okay, I am going to write this equation in matrix form like this. So what we are writing, this equation I have got A1 d by dt plus A2, this is one term, B1 d by dt plus B2, here A3 d by dt plus A4 and B3 d by dt plus B4, this into V dash R dash equal to 0 0. This was my equation. See, this into this plus this into this 0, this into this plus, okay. And the characteristic equation is formed by taking the determinant of that, and if you take a determinant of that, something like when you say A sigma square plus B sigma plus C equal to 0, and A actually is a term having proportional to, see, if you expand that, there will be term proportional to d by d square by dt square. So, it will be A1 B3 d square by dt square plus A3 B1 d square by dt square. That means basically you are going to have A1 B3 plus A3 B1 d square by dt square, like that, something into d by dt plus something. This is what we will call A, this is what is called B, this is what is called C. I mean, again we are not going into the detail of the numerical method of solution, etc., etc. All that I want to tell you is that this kind of equation has a standard solution expressed by the solution of them will look like that, when I, of course I do not know what is V1, I do not know what is V2, but it will be exponential with sigma 1 sigma 2 on the top, when sigma 1 sigma 2 are supposed to be roots of this quadratic equation. Characteristic equation, this A, now this we are finding out from here. See, this is A, this is B, this is C, and the characteristic equation is A sigma square plus this sigma plus C equal to 0. Obviously I know what is A, B, C. A is A3 A1 B3 minus A3 B1. B will be of course much longer term, because B will be d by dt. See, it will be A2 B3 and then A4 B1, then A3 B2 and A1 B4. There will be 4 terms coming, and the other one will be of course A2 B4, A4 B2. And again remember, A1, A2, A3 are all actually long terms, because they are all in terms of this this big coefficients. So, you end up getting actually a characteristic equation where A, B, C are long. In fact, I will just write what is A, one of the term of A. You see, A for example will turn out to be I z dash minus A naught dot dash, in fact that is what it is, into m dash minus y v dot dash minus y r dot dash minus m x g dot and n v dot dash minus m dot x g, something like that. Let me see whether this is right, because this, let me see, this is A1 A3, no, this will be y dash minus this into this, let me know, A1 into we had into this one, so m minus y v into I z, this into this, see, this is A3 A4 B3 B4. So, A1 B3 is okay and A3 B1 is okay. Yeah, see, that is how what it is. See, this is my A1, this is my B3 and this is my B1, this is my A3, like that, you know. So, what I am trying to say that it is only longish algebra, okay, but there is nothing conceptually difficult about it. It is simple, you know, you might have a long algebra, but there is nothing more difficult. I will write the C. B is actually much longer, so we do not write B, because B will have actually, here are 2 terms, but there B has got 4 terms, so it goes for a long time, no point. You can write like that. Say C, I write C is y v dash into n r dash minus m x g, something like that, minus y r dash minus m dash into n v dash, something like that. In fact, you can make it out from here also, because here actually it is this one, this one into this one. So, n v you can, yeah, nr minus sorry, where is yv here, yv into nr minus mxg, yeah, this first term, this 2, and then this one nv into this one yr minus m dash. Okay. See, this is this. I mean, you can make it out. There is really not there is nothing conceptually difficult on that. It's very straightforward thing. So we end up getting this. Okay. Now comes the stability criteria. That is very interesting. You see, now I have got now we have to look very carefully. See, we have got here solution of v dash equal to v1 e to the power of say plus minus sigma I t I can write, or say v1 e to the sigma 1 t plus v2 e to the sigma 2 t, and r dash equal to r1 e to the sigma 1 t, r2 e to the sigma 2 t. Okay. Now you tell me, see what we want. We want the ship to be stable. What should be the criteria for sigma 1, sigma 2? That is what we have to now look for. Okay. No. Now what we see, now let us take one by one. If sigma 1 is real, sigma 1 is imaginary, that means sigma 1 is become I sigma. Then what happens? The solution is a sinusoidal. Then it goes like that. See, when you have e to the I theta, that is cos theta plus I sin theta. So if this is imaginary, okay, then what happens? You don't have a decaying solution. You may have a decaying solution, but you cannot actually say this part won't give a decay. Decay can only be from this side. See, we will look into that one by one with one part. Supposing I take a condition of something into e to the sigma t. Okay, what is sigma? Say sigma is imaginary. Then what happens? This becomes a e to the say I into say sigma star t. This is nothing but a into cos sigma star t plus I sin sigma star t, or it becomes a sinusoidal. So this becomes a sinusoidal solution. There is no decay. Remember, the decay would have been if A was decaying. If A was having a sigma t, which is what happened in the damping case, in damping case, you have got minus t into cos omega t. So this decays, but this is not decaying. This is the sinusoidal curve. So remember that if sigma therefore becomes imaginary, then you cannot have it doesn't decay. Now I have got, see, but my case is actually A1 e sigma 1 t plus A2 e sigma 2 t. So I can have one of them imaginary and one of them real, but even if one of them is imaginary, I have a decaying like a sinusoidal solution. So I don't want it. That is number one. So I don't want sigma to be imaginary, either one or both. Or now let us say what is sigma 1's value of positive negative. Let us say one of the sigma 1 is positive. Then what happened? This one will grow. Suppose sigma 1 is positive, then with time this one grows. That means R and V are increasing. Even though the another is negative, remember that one part is positive, so it is going to grow. So the only possible solution that I want for the ship to be stable is that both sigma 1 and sigma 2 must be real negative. Okay, this is what we are trying to talk about. Now we have to find out what criteria causes that to be real negative, and then find out that translate to what characteristic of the ship. This is what we are looking at. But this is a very important concept. So you see, we must sort of emphasize that for V dash and R dash to reduce with time and eventually become 0, approach 0, sigma 1, sigma 2 must be real negative. This is very important. Okay, that means my solution, this, see, I have got this. What is my solution for this equation? See, what is sigma 1 and 2 equal to minus, you see, b by a plus minus by 2. This everybody knows, no? See, No, actually I no this is actually b square minus 4ac by 2. Okay, there is a root over of this is a root over, right. Basically a solution of I wrote this fashion, but actually it is b square minus 4ac by 2a. No. B
minus b plus minus root over b square minus 4ac, yes.
Something like that. It is a standard thing. So I just wrote that by b by 2a, I mean, etc. etc. The reason is because we want to know what is the characteristic of b by a and c by a, because you see it can be written in terms of b by a and c by a. We want to make sure that this is all real negative. That's all we want to make sure. Okay, that. Now we have to find out, now we will write it down again in the next page, because I want to write very carefully and you to understand what must be the criteria for c by a and b by a for this to be both to be negative. That is what we have to find out. Okay. See, again I will write down, we have got sigma 1 and 2 is equal to minus b by a. Let me say 2 times of that, because you know that 2 I can always take this side, so that I do not have to write this bottom 2 again, b by a square minus 4 c by a. Okay, that below 2 was there, I took the 2 this side. Now you see, we want sigma 1 sigma 2 to be all negative. Now this is negative, remember. So now I have got the choice. Let me just think of the cases that see, I have got two numbers b by a and c by a. So I can have b by a positive, c by a negative, etc. I mean positive positive, negative negative, positive negative, negative positive. Let us think of all that thing. Let us see about say c by a. Say c by a is 0, greater than 0. No. Let me say c by a is less than 0. Now if c by a is less than 0, you see, minus 4 c by a becomes a positive number. Okay. If c by a is less than 0, then this becomes a positive number. B square by b by a square is a positive number. So this is a positive number. Now you have got a positive number. Now you tell me what happens. This is a positive number of a magnitude more than b by a, because you see it is b by a square plus another number. So suppose b by a is say 2, then this is going to be say more than 2. Now here I have got minus b by a minus that number and minus b by a plus that number. So there is one, see this, in this case I can write it that b by a square minus 4 c a root over it is b by a plus some epsilon, some small number. Obviously it will become more than b by a. Therefore the roots becomes minus b by a minus b by a minus epsilon and minus b by a plus b by a plus epsilon. This is negative, but this is positive. So I end up having one positive number. I cannot have it. Therefore c by a has to be negative. That is point number 1. 2. This of course is obvious. B by a. B by a obviously has to be this thing here the b by a. What b by a should be? Now b by a has two choice, positive and negative. Let us say b by a is negative. Okay.
So then whole thing will become positive.
Again, then what would happen? This becomes negative means square here, minus something here, then whole thing becomes positive, as you say. Therefore this is not possible. So for the criteria I must have b by a to be positive.
Or we can straightaway put that b by square minus 4 is equal to 0.
Yeah, okay. No, that's okay. What we want to know.
But is 0 will get negative.
Which one?
Real negative. If b by a whole square minus 4ac is 0.
Okay.
Then we will get the whole part as.
Yeah, that's okay. Then you have got minus b by. No, that we don't know. You see, what we are trying to find out is we don't know that. What we want to know, what we can find out is that, see, first one I found out that if c by a is less than 0, then I have one part solution. Therefore this cannot be positive. Therefore c by a must be this thing. This is one of the criteria. C by a must be more than 0. See, if c by a was less than 0, I found out that one of the solution, one of the roots becomes negative, positive. We cannot have it. So if the both the roots must be negative, then c by a must be positive. Now b by a. If b by a is negative, we will find out that this negative square, of course, is a positive number, minus whatever this number is, negative number. So, this can be actually smaller than b by a or larger than b by a. See, now we have got c by a to be positive. So, therefore, obviously b by a square minus, see, we have said that c by a is positive. Now, if this is negative number, so negative square, this is a positive number obviously, and this one. So, again the same criteria will come, because this term will become more than b by a plus epsilon, because you see when you take a negative square becomes positive number. So, if b by a was negative, then again I end up getting one solution which is positive. So, b by a also, this is not possible. So, b by a also must be positive. Why? Because if b by a is positive, remember that, then this is negative. So, there is negative minus negative, negative minus another number smaller than that. So, we end up getting like this, okay, because this is actually what happened. Remember, this is actually positive, therefore, this is less than that. Okay. So, you end up getting the criteria that my both sigma 1 sigma 2 will be your negative, provided sigma 1 and sigma 2, I mean let me do are negative if b by a is greater than 0, c by a is greater than 0. Okay. This is now my criteria. We will keep that right now, this b by a greater than 0, c by a greater than 0, and we will discuss that little later after we talk about hydrodynamic derivatives at little more detail. What is b by a, c by a? B, a, c are all function of yv, dash nv dot dash yr dot dash nr dot dash, plus of course I dash m dash xg dash etc. Okay. These are of course rigid body parameters. So, we are not I mean these are of course important, but rigid body parameters, but these are the terms which actually tells me how a fluid force reacts or acts if there is a flow around it. Now, what we need to do is to actually talk about this at slight greater length, that I will want to talk about that little bigger length. See, we understand this now. Okay. Now, let us we will come back to the, as I say, stability criteria. We can say this is my stability criteria. For a shape with a control fixed, controls are fixed. I do not have a control line, but in such a case for the shape to have the come back to its original path of straight line. Remember that it is only straight line stability, because when v is 0, r is 0, which means it is not further turning, but it is not changing its heading. See, the ship was going in this direction. Now, you have got a disturbance. So, it actually eventually comes back and begin to go on a straight line. When it goes to a straight line, you have got v dash 0, r dash 0. So, it simply ensures that the shape can go in a, finally it goes to another straight line only. That is important, because it is not positional stability, directional stability, but straight line stability only. All that we are saying is that if there is a disturbance, the ship could have actually gone hayward, but instead of that, it when you remove the disturbance, it actually begins to go again along another straight line, because going along the straight line implies v dot 0 and r dot, I mean v and r both, there is no v, no motion in the y direction, no motion around z direction, all that. So, we have to therefore relate this condition with those parameters, and let us now look back at these parameters little more deeply, because this is what is called hydrodynamic derivatives. Okay. Then I will come back, because we have to relate stability criteria with the derivatives. Then what happens, if you can find the derivatives, then you can tell that, look, this ship has this derivative and this satisfies this, so the ship is going to be stable. Just like when Kg and Gm, like Gm is positive, the ship is stable. Now, you see all this term, I am not writing here that this thing, If you see here, we have got y and n, and we have got v, v dot, r, r dot. Basically, derivative of this with any of them is my hydrodynamic derivative. Your moment, your force against sway velocity, your force against sway acceleration, etc., etc. Now, these are called the hydrodynamic derivatives because they represent basically a hydrodynamic force on the hull because of any of these motion parameters. These are my motions, velocity plus acceleration. This is my force and moment. So, derivative of force and moment against any of the velocity and acceleration, of course yaw and sway, is what we call hydrodynamic derivative. What is the meaning? Take a ship here. I try to give a push. I try to give a V here. Okay. Moment I try to give a V here or V dot here, say V dot here, I am basically shifting it that side. Fluid is going to give a pressure. This net pressure will add up to a y force. So, given V I have got a y, given V dot I have got a y, given V I have got also maybe an n depending on the direction, and given V dot I have got an n. So, if I now plot this V against y, V dash against y and take the slope, then I am getting this derivative, because when I say yv it is dy by dv. So, that means that if there was an actually velocity of v, my force would have been this into this, right, because you see what we are doing is that this is my v, this is my y, this is my slope here. So, this value is yv into v, because yv is the slope. This is what the idea is. Okay. So, hydrodynamic derivatives essentially are hydrodynamic forces that are introduced on the body because of introduction of some motions. In fact, you can call the resistance to be also an xu hydrodynamic derivative, because you see it is the x force because of u velocity. In a sense, one can always tell that, that you see it is the resistance is something into v square or something. So, that means there is a v there, because if there is a v u square, let us say forward velocity, r is there. That means you can say that there is a coefficient of v square. So, one can also think in terms of a derivative. It is something similar to that. We do not use the term derivative because derivatives are supposed to be small numbers, but it is something similar to that. What we need to now do is to now check one by one what would be the typical magnitude. We do not know it, what may be the typical magnitude and what may be the typical sort of sign, plus or minus sign for these derivatives. You see, we can find out by a study, by qualitative study, which is what we will do now for next some time, which direction yv is. That means, or all this term, is yv positive or yv negative? Number one question. Number two, is yv a large positive or is yv a large negative for a typical ship? We will find out that regardless of ship, some of the numbers are always large, some of the numbers are always negative, some of the numbers are always positive, regardless of what the ship is. Because if that is the case, like if you can find out, then you can actually use that to this stability derivative, because this b and a, as you know, are long terms. This b equal to a1 b2 minus etc., and a1 b2, each one of them is again long derivatives. So, this turns out to a large number of derivatives. See, b and a, if you look back, a and b are in terms of a1 b1 a2 b2 a3 b3. So, that means b may be b2 b4 minus a1 a4 etc., and each of them again is like depending on nv yv minus. So, if you write this, it will become a large expression. So, we want to now, since we know these two criteria, we want to reduce that to a more selected criteria based on the hydrodynamic derivative idea, because some of the derivatives you will find out has some typical number. It is of either a large positive, large negative, etc., etc. That is why the concept of derivatives is important. So, we will just start on that and go one by one. Let us look into first yv, yv dot and yv. Okay. Now you see, it is very important that we have got a proper axis system drawn. This was my x, this is my y, and rotation obviously would be x to y direction. So, this is my positive y force, positive v direction, and this is my n and r direction. Okay. We do not need n and r right now, so I need not have written n and r, forget it, but this is what it is. Now think of yv. This we are doing going to do slowly. Yv is what is my y given a v. Okay. Now let us say that I give a v which is negative, I give a v in a negative direction. So v is negative. I have pushed the body on the other side. What would happen? You are going to get all that forces acting over the entire hull in this direction. Okay? That is agreed. Then what happened? You end up getting a force. Which direction the force will come? Force will come this direction. So you are going to get a positive y for a negative v. In other words, if I have to plot here now v here and y here, I will get a positive y for a negative v. That means the graph is going to look something like this. That is one. Therefore, yv is negative, no question about it. Is it large or small? Question is that here at every point, let us call this to be stern region, let us call this to be like stem region, stern region, forward region, aft region. Forward and aft in entire part my force is acting in one direction. Okay. Entire force is the full fluid is trying to push it in one side. So what happens? It becomes a large negative. So this becomes a large negative. See, now what happened that as I am going in this direction, my fluid is getting, I mean the entire fluid is trying to push it on this direction. This push acts over the entire part of this longitudinal length. The full length gets pushed down. Now let us say we can call it separately, say that this plus this plus this plus this all are added up. Obviously, when you add them all up, then you get a large number. Supposing this was pushing and this was pulling, and it was this plus that could have been a some number minus some number, could have been either positive or negative. But in this case it is not so. The entire hull, each point on the side facing gets a push. So I get a large force when you add them. I think I will explain that more with a v dot rather than v. Okay, because that will be more easier. See, if I give a v dot here, same thing I am giving an acceleration. So I am again going to get all these forces on this side, all of them. See, I am trying to accelerate that. Okay, accelerate that side, so I get all the forces this side. What would happen if I draw v dot? Also I get a large y. Okay, so I get yv dot to be large y, negative. So I get yv dot to be negative. Okay, now is it large or small? I want to answer you this question. See, yv dot is nothing but like an added mass. Yv dot is actually, because I am given an acceleration, this side there is a reaction force. So you can say that the full fluid gets trying to get accelerated on that side, which will give you an inertia for opposite side. Because you see, if I took this body and I try to accelerate on this negative acceleration, then I get a mass into acceleration force on the negative direction. So that is why I get minus yv dot v dot. I get a force of minus yv dot v dot. This is like added mass into acceleration, and added mass in sway and surge are of the order of the mass for this, because
why we are considering v and v dot as negative, sir?
No, it can be positive. Because I gave an example where if I give a v dot negative, then I get y positive. Okay, you give a positive v dot, you will get a force on the other side. This is the mood debate. I will have to end now. See, if you give a v here or v dot here, then you get a force on this side. The question here is that whichever direction you give v, y is on the other direction. Okay. Anyhow, we will pick up on that again in next like class, because this lecture time is up. We will pick up on that again. Okay. So I'll end this one at this point. Okay, we will continue our talk on the same topic. Derivatives, stability criteria. This is the directional stability. No, so again I will just bring back my last class and the last lecture. This slide. The reason I want to bring it back is to tell you that what we were talking, that whichever direction you give v and v dot. See, normally what happens, if you give a velocity in direction 1, then the y is going to be opposite direction. If you motion in v dash direction, will be opposite direction. Therefore, number 1 is that both yv and yv dot are negative. See, this and this both are negative. That we know.
So why you are telling negatives?
Oh, okay. Why? Oh, okay. Why? Okay. Now I understand your question. Why I'm taking negative? You see, if you give plus y, it gives, no, rather I'll tell you this on the other side. Plus v gives minus y, minus v gives plus y. So if you do a plot here, v and y, the plot will look like this, like this. This slope dy by dv is always negative. Minus by plus or plus by minus is always negative. Okay. That is why similarly dy by dv dot always negative. This is why it is always negative. Not only that we know it is always negative, it is also a large negative. So it is, see, I can say that yv dot is large negative. In fact, this is of the order of mass, because it is added, it is sway moment of inertia. In fact, you see that equation is written m dash minus yv dot v dot. You see, you would have actually, it is interesting because you would see in our other equation, it was mass plus added mass into acceleration. Okay, that was the equation. So this has become the added mass. Minus yv dot is added mass, not yv dot. See, yv dot is negative. So minus yv dot becomes added mass. Analogically, if you compare with, say, heave and sway and all, see, if you look at their equation of motion, if you actually look, I'll just give more examples. See, we had got here m z dot dot equal to minus fact that origin is not coinciding. You remember one thing is that, see, that if I took an axis here, then my stance time definition differs, and then I have got large xg dash. Normally, if I took the xg dash here, then see, xg dash is such a point from where the stamens are almost same distance. Therefore, the origin that we take, okay, from that xg dash is very small. Therefore, this can be small, and in fact, I can neglect that if I took the origin at xg dash. In fact, sometimes people do that. I mean, if I took the origin at g, g is not too far. You see, g is not like 20 meter ahead of midship, maybe 2, 3 meter, 3 meter ahead of midship. Okay, that is also true. So regardless, this becomes a small number, and this also becomes a small number because it's nv dot. Does not matter, even though it is little large or so, but this is small. See, this is much large, this is much large. This will be much smaller as compared to this terms. So whatever happens to this and this term,
M dash you are telling large, but m dash g dash quite small. Sir.
m dash into xg dash. M dash is large, but xg dash is very small. It can be 0 also. See, no. See, this is large by this. See, let me put it this way. Let us not take the dash terms. Okay, let us take that suppose now term. Now m is actually, say, mass 20,000 ton. This is 20,000 ton multiplied by 2 meter or so. Of course, is non-dimensional. So there is a v term, that L term comes in. In fact, if you take that, no. This the units are not taken. See, this dash, there is some kind of unit. There was a u here that we didn't take. If you take it properly, this will be a small number. It is not. You see, this is 20,000 ton. Okay, in a mass, but this has got, because I have taken a dash. If you didn't take a dash, there will be another term that will come in, so that the dimensional equivalence is there, regardless of the fact that this remains a small number. Okay, and if you take a non-dimensional value, say this is a large, but it will be let us say 0.02, okay. This is supposed to be large because you are multiplying with half rho L cube. This is 0.02, but this is going to be 0.00 because it is xg by L, you see 2 meter by 100 meter or 2 meter by 200 meter. So, it is 0.001 something like that. So, that this becomes much smaller. Regardless of that, unless it is of the order of 1, this will not cancel with that. See, m dash and m dash x, you compare this term, this and this, okay. These and these are same, but this is of course xg by L, which is of course much smaller than 1. Therefore, such that we will find out later on that this will cause, if I give a yr, if I give a delta R to be negative, the ship is going to turn on the other side. It is actually devised such a way that if you turn it this side, the ship turns on the other side. So, that analysis we will do afterwards for a steady turn. If you want to actually show the transient, you have to solve this full equation, which cannot be solved so easily, okay. You can solve in a time domain, like step by step simulate, like give a force, see how the trajectory is. So, this is about the rudder part, and I wanted to say that actually if here you will find out an interesting part, that what remains here, this part and this term, you will find out that actually this two and this two have a relation with respect to my stability criteria. The stability criteria, if you look back, I will just show you a little bit. It contains of nr yv, nv yn minus n, that is where it is nr y, wait now, yv here, oh this v dot, nr, yeah, what I mean is that we can actually show that there will be a this r dash nr and yv, this multiplication, and this will come. One can show that basically this criteria have a relation with this rudder angle. In other words, only for a stable ship, I'll do that afterwards. Only for a stable ship, you will find out that if you give a rudder this side, the ship turns that side. In other words, you are actually assuming there is a stability involved somewhere. Anyhow, that we will discuss in the subsequent class with respect to our definitive maneuvers. But this is where I will stop here. So, what I want to sum up here therefore is that we should understand that there is something called stability criteria, which is an intrinsic property of the hull. These are intrinsic property of the hull. So, therefore, if you have a bad hull design which has an intrinsically unstable hull, then obviously you will need much more rudder control to make